Hello everyone, good evening. Good evening, good evening. So I think my video is clear, right? So I'm audible and my video is clear. Okay, so we'll start our first video on a PYQ series. We'll be starting linear algebra first, right? So I'll be solving some last 10 years papers of UPSC Mathematics optional. So already if you go to playlist, linear algebra, some part of linear algebra is already covered. So if you haven't know the basic concepts, you just go to the playlist and watch. There will be a playlist named as linear algebra 2.0, right? You see that video. So we will start 2024 solutions of linear algebra. So this 2024 question paper has 5 questions overall from linear algebra and it carries 70 marks, right? So linear algebra is one of the easiest subject. If you know the concept, you can easily get 70 marks, right? Very easily you can get 70 marks surely. Usually from linear algebra, you can expect 60 to 70 marks every year, but 70 marks we can expect more frequently. You can easily get 70 marks like that kind of subjects, right? Okay, I'm assuming that everyone knows the basic idea of linear algebra before starting PYQ series, right? If you haven't know the basics of linear algebra itself, you just go to the playlist and watch the videos of linear algebra, right? Okay, so there are 5 problems, so I'll try to finish this in 1 hour or 1 hour 10 minutes. So we'll start with the first problem of 2024. Yes, so let H be a subspace of R4. So let H be a subspace of R4 spanned by this vectors. So we can see V1, V2, V3 are the vectors of R4, and we have subspace H, and that subspace is spanned by these 3 vectors. Then find the basis and dimension of H. Extend the basis of H to a basis of R4. See, this question carries 10 marks, but it is not at all that difficult. Very, very simple questions, right? Think of writing theory questions 10 marks, right? You have to elaborate, you have to think, but this is just a problem solving. That is 10 marks. Okay. So we have let H be a subspace of R4. So we have a H, and this H is a subspace of R4. So H is a subspace of R4, right? And this H is spanned by these 2 vectors, right? H is spanned by these 2 vectors. So that is H is nothing but this subspace H is spanned by V1, V2, V3. Now what we'll do is we will find the dimension of S, right? So we'll find the dimension of S. So you can write V1, V2, V3 as in a row format or in column format. That is your wish. If you try to write in a row, you are finding row space. If you are finding if you are writing in a column, you are finding basis for column space. That not an issue. So let us try to write this. Let's try to write this H as row. So we'll have 1 minus 2, 5 minus 3. So 2, 3, 1 and minus 4. And we have 3, 8, minus 3 and minus 5. So we need to find the dimension of S. So what you have to, so in order to find dimension of a subspace, dimension of some vectors, you just reduce this to row echelon form and you find the pivot element, right? You reduce this to row echelon form and you find the pivot element. So first you try to reduce this to row echelon form. So we have R2 is transformed to R2 minus 2 times R1. R3 is transformed to R3 minus 3 times R1. So you can see this is equivalent to 1 minus 2, 5 minus 3. Now R2 is transformed to R2 minus 2 times R1. So you multiply 2 and then you subtract. You multiply 2, this will be minus 4. So 3 minus of minus 4 will be plus 7. 1 minus 10. 1 minus 10 is minus 9. And minus 4 plus 6. Minus 4 minus 4 plus 6, it will be plus 2, and then R3 minus 3 times R1, this will be 0, You multiply 3 and then you subtract. So this will be minus 6. So 8 minus half minus 6 will be plus 14. So minus 3 minus 3 minus 15. Minus 3 minus 15 is minus 18. Minus 5 plus 9. Minus 5 plus 9. So this will be 4. Right? So we'll again we'll reduce this to row echelon form, right? So when a matrix is said to be in row echelon form, so first row, non-zero element, below that everything has to be 0. Yes. First row, first non-zero element. Below that column, everything has to be 0. So first row, first non-zero element is 1. Below that everything is 0. Now go to second row. Second row, first non-zero element is 7. Below that everything has to be 0. The corresponding column, but it is not 0 here. So we will make this element as 0 with the help of this element. So these are just 12th standard level mathematics, right? I'm assuming that you know the idea of row echelon form. So we have R3 stands for 2, R3 minus 2 times R2. So if I perform this operation, you can see this matrix reduces to 1 minus 2, 5 minus 3, and then 0, 7, minus 9 and 2. You subtract, you multiply 2 and then you subtract. You multiply 2 and then you subtract. So this entire row will be 0 row, right? Now this is in row echelon form because first row, first non-zero element is 1. Below that everything is 0. Second row, first non-zero element is 7. Below that everything is 0. And third row, there is no non-zero element. This is in row echelon form. Now, you just you make this our pivot element, right? This is our pivot element. That is first row. In each row, that starting element is our pivot element. Each row, first non-zero element, right? Or else you can write this as 1 minus 2, 5 minus 3, 0, 1 minus 9 by 7, 2 by 7. I'm just dividing this by 7. This is 0, 0, 0, 0. Now you can see what is the rank for this. What is the rank for this matrix? The rank for this matrix is 2. Rank will tell you the dimension. So that means dimension of H is 2. Even though there are 3 vectors here, these 3 vectors will span only 2-dimensional space. That is, it will span only R2, but we need to span R4, right? So dimension of H is 2. And what is the basis for H? See, basis for H, there are many bases for H. Any linearly independent set which span H will be a basis, right? So how to find a basis? You just see, you see, there are many bases. Someone will say that this row and this row are bases. Yes, that is a basis, right? The first, because this is a you select all non-zero rows. That is 1 minus 2, 5 minus 3, and 0, 7, minus 9 and 2. See, basis has 2 elements. Number of elements in the basis is the dimension. So dimension is 2 and these are the 2 vectors that will span H. These are not only the 2 vectors that will span H, right? Or I can also write basis of S to be. Now you see the pivot element, right? You see the pivot element. So first row as a non first row as a pivot element, second row as also as pivot element. First row as pivot element, second row also as pivot element, but here there is no pivot element, right? One is not here. So first row as pivot element. What is our first vector? V1, and the second row as also as pivot element. What is our second vector? V2. These two also a basis for H. These two vectors will also span H. Or 1 minus 2, 5 minus 3, 0, 1 minus 9 by 7, 2 by 7. This vector will also form a basis for H. Basis need not be unique. Any linearly independent set which is span this H will be a basis. Right? Basis need not be a unique basis, unique set. Right? Or basis of H can also be V1, V2. V1, V2 are the vectors you already know. Okay, then find the basis and dimension of H. So dimension is 2, basis can be this or this, anything. Right? Okay. Now we can see that this has dimension only 2. In order to span R4, R4 has dimension 4. That means you need 4 linearly independent vectors to span R4. But here we have only 2 linearly independent vectors. You add 2 more linearly independent vectors. What vector you need to add? You add any 2 linearly independent vectors, right? That will span R4. So uh, extended basis of H. Extended basis of H. So already we have 1 minus 2 5 minus 3 0 7 minus 9 and 2. You add 2 more vectors so that all 4 will be of dimension 4. So let us add the vectors 0 0 1 0 0 0 0 1. Now you can see this is of dimension 4. How to check it is of dimension 4? You just reduce this to row echelon form. In that row echelon form, see, actually already we have this, right? Already if I reduce this to row echelon form, we have this. So instead of this 0 0 0, I'm adding 0 0 1 0 0 0 0 1. In that case, your rank will be 4, right? So I'm adding two vectors such that rank is 4, right? So that means you just see here, I'm extending a basis to be like, I'm extending a basis to be like, already we have 1 minus 2 5 and minus 3, and then we have 0 7 minus 9 and 2. This is of dimension 2, right? I'm just adding two more vectors 0 0 1 0 0 0 0 1. So if I add this, you can see this is of rank 4 because it has 4 non-zero rows, right? So I'm adding these two vectors so that this will be of dimension 4 and it will span R4. That is the idea, right? Okay, so extended basis of H's, I'm adding these two vectors. See, it carries 10 marks. Actually, if you know the concept, you can do this in 2 to 3 minutes. Very simple idea. Okay, so we'll move on to the next problem. So what this problem says is H be a subspace of R4 and H is a subspace of R4 which is of dimension 2 and basis is any two linearly independent vector which is span H. So basis, your friend basis and your basis need not be same, right? But it has to be linearly independent and it has to span H. So these two are bases or these two are also bases and the extended basis is I'm adding these two vectors so that it will be of dimension 4. Therefore, it will be a basis for R4. Okay, so we move on to second problem. Let T is a map from R3 to R3 be a linear operator and B be the basis B1, B2, B3. We don't know what B1, B2, B3 are, but it is a basis of R3. And suppose that, see, we don't know the map. We don't know what is T of x comma y comma z. T of x comma y comma z they have been given explicitly. But in that operator, if you substitute T of V1, you'll get output as 1 0 minus 1. T of V2 is 1 0 minus 1 and T of V3 is 2 1 minus 1. We don't know that map, but that map takes V1 to 1 0 minus 1, V2 to V2, it takes V2 to 1 0 minus 1, both are 1 0 minus 1. I think there is some error in the question, just a minute. Just a minute. T of 1 0 minus 1 1 1 0. Just a minute. Yes, so we'll start. It is T of V1 is 1 1 0. So V1 T of V1 1 1 0, T of V2 is 1 0 minus 1 and T of V3 is 2 1 minus 1. Yes. Find the basis for range space and null space of T. So we don't know the operator, but that operator takes V1, V2, V3 to the corresponding this matrix, right? So we have what is the matrix of T with respect to the basis, right? The matrix of T with respect to the basis is 1 1 0, 1 0 minus 1 and 2 1 minus 1. So this is the corresponding matrix that operator takes that basis vector. We need to find the range space, find the basis for range space. So we will try to find the range space for this. That is, we need to find the range for this matrix. So how to find range space? Again, very simple. In the previous problem only we did we have found the range space. Hey, range space nothing but basis for rank, basis for this row echelon form. Okay, so we'll reduce this to row echelon form. So R2 is transformed to R2 minus R1. R3 is perfectly good. So we have 1, 1, 2, 1, 1, 2. So 1 minus 1, 0, 0 minus 1, 1 minus 2, so 0 minus 1 minus 1. So this is equivalent to 1, 1, 2, 0 minus 1 minus 1, 0, 0, 0, right? R3 is transformed to R3 minus R2. So this is in row echelon form, and you can see this is in row echelon form, right? This is in row echelon form. This is in row echelon form, and what is the dimension of this? What is dimension of T? It is nothing but what? 2, right? 2, and what is the basis? You just write these two vectors. Basis is 1, 1, 2, and 0, minus 1, and minus 1. So these two vectors will span the range space, and there are two vectors in the range space. So that means dimension will be equal to 2, right? Yes. Now what we need to do is we need to find the um, null space, right? We need to find the null space that we will do now. Yes, just a minute. Okay. You can also write this instead of column. You can also write it as row, right? You can also write it as row. If you write it as row, the base will be different. But any two linearly independent vectors um, that span this range space will be a basis, right? Don't worry about that. Okay. Now we will find null space of T, dimension of R of T. Okay. Now we will find null space of T. So what is null space of T? You collect all those vectors in the domain R3 such that Tx is equal to 0, right? You collect all those x such that Tx is equal to 0. That is, you collect all those x that linear maps takes to 0 vector of codomain, right? That is, you are collecting all those x that maps to 0, right? You're collecting all those x that is mapping to 0. So all those x that is mapping to 0, you put it in one set. That set is called null space of T, right? You collect all those x in R3 such that T of x is equal to 0. Now we will find all those x such that Tx is equal to 0. So what is T? T is 1, 1, 0, 1, 0, minus 1, 2, 1, minus 1. And what is x? X is a vector in R3. Let us call it as x comma y comma z, and it takes to 0 vector. This is a 0 vector of codomain. So 0 vector of R3 is 0, 0, 0. So this reduces to a homogeneous system, right? Ax equal to 0. So we will solve this homogeneous system. That solution will be the null space of T. So we have, uh, so we will solve this homogeneous system. We solve this homogeneous system. We solve this homogeneous system to find the null space. So for homogeneous system, we will solve augmented matrix A comma 0. So 1 1 2 0 1 0 1 0 0 minus 1 0. So reduce this to row echelon form. So this is equivalent to. So we can directly write this step, right? Because if I do R2, this matrix is same as this, right? So this is equivalent to 1 1 1 1 2 0 0 minus 1 minus 1 0, and then we have 0 0 0 0. Now we can see this is in row echelon form, right? This is in row echelon form, and you can see this is in row echelon form. We have rank of A and a rank of A comma B, both are equal to 2, and it is less than total number of variables. It means this system has infinitely many solutions, right? This system has infinitely many solutions. Now we will find all those solutions. These are just a very simple idea to solve homogeneous system. If you haven't know, let's go to the playlist and watch the system of equations video. So here we can see number of free variable. The number of free variable is equal to n minus rank of A. So total number of variable is 3, rank of A is 2. So we have one free variable, right? We have one free variable. And if you reduce this, if you write that this back to the form Ax equal to 0, if you write this back to the form Ax equal to 0, we have, so we have two equations, right? We will write this in this form. So 1 1 2, and then 0 minus 1 minus 1, 0 minus 1 minus 1, then we have 0 0 0, and then we have x comma y comma z is equal to 0 0 0. So we have x plus y plus 2z is equal to 0, minus y minus z is equal to 0. So let us assume, see there is one free variable. Let us assume z is equal to k, right? Let us assume z is equal to k. If z is equal to k, we have minus y is equal to z. So that means y will be minus k, y will be minus k, and x is minus y minus 2z. So minus y is minus k, z is k. So we have k minus 2k, and x is also k. Therefore, the solution space is given by, that is x comma y comma z is given by, so x is minus k, and y is again minus k, and z is k. So that means if I take k outside, minus 1 comma 0. So you can see any multiple of k times minus 1 comma minus 1 comma 0 will be in our null space. Why? Because you put any, for example, you put k is equal to 1. If k is equal to 1, then you will have minus 1 comma minus 1 comma 0. So minus 1 comma minus 1 comma 0 will satisfy all three equations, right? Minus 1 0. So minus 1, sorry, this plus 1. So minus 1 comma 1 1 will satisfy the equations, right? Minus 1 is minus 2. Minus 2 plus 2 is 0. minus y minus z. So this is 1 minus 1 is 0. You multiply 2 times of this. You put k is equal to 2. So minus 2 plus 2 will satisfy this equation. And this is our null space, right? So null space consists of k times minus 1 comma 1 comma 1, and this k belongs to real number. And you can see this single vector alone spans the null space. This single linearly independent vector spans the null space. So number of elements in the basis is 1. That means this is our null space, and the dimension of null space is equal to 1. So null space, the basis for null space is this, right? The basis for null space is minus 1 comma 1 comma 1. Basis for null space is nothing but a single vector minus 1 comma 1. So any multiple of this will be in the null space. Uh, or else you can also find, like, you can also use rank nullity theorem. You can also use rank nullity theorem also. What the question says is find the basis for range space and null space. The basis for range space is these two vectors, and the basis for null space is minus 1 comma, why I'm doing like this? This is minus 1, minus 1, 1, right? Minus 1, minus 1, 1. So minus 1, 1 is our basis for null space. And all, but suppose if they ask you to find the nullity, that is, if they ask you to find instead of basis for range space and null space, if they ask you to find rank and nullity, rank we already know because dimension of range space is our rank. So rank is 2. So what rank nullity theorem says is rank of t plus nullity of t is always equal to the dimension of our domain space. Dimension of our domain space. So our dimension of domain space is 3, rank is 2. So nullity has to be 1. But we are getting nullity will be equal to 1. But dimension of null space is called nullity. Dimension of range space is called rank. Right? Dimension of range space is called rank. Dimension of null space is called nullity. So dimension of basis for range space is this, and the basis for null space is minus 1, and 1. So we'll move on to the next problem. Okay, so we'll move on to the next thing. Consider a linear operator T on R3 defined by T of x comma y comma z is 2x comma 4x minus y comma 2x plus 3y minus z. Is T invertible? If yes, find T inverse. When a matrix is invertible, see, this operator is invertible if the corresponding matrix is invertible. Both are isomorphic. If this operator will be invertible if the corresponding matrix to this operator is invertible. And we know when a matrix is invertible if it is non-singular. That is, determinant of that matrix is not equal to 0 means it is invertible, right? Okay, so we'll move on to the next problem. So we'll start little bit fast, right? I think I'm taking a lot of time. I'll do this little bit fast. So consider linear operator T on R3 by R3. See, here they haven't mentioned about the basis. So we just take the standard basis. So we'll find the corresponding matrix for this linear operator. So we'll find the matrix of T with respect to the standard basis. So T of 1 comma 0 comma 0 will be 2 comma 4 comma 2. And then T of 0 comma 1 comma 0 is given by standard basis of R3 is 1 0 0 0 1 0 0 0 1. So T of 0 comma 1 comma 0 is 0 comma minus 1 comma 3, and T of 0 comma 0 comma 1 is given by 0 comma 0 comma minus 1. Now how to represent this as a matrix? Now you express this vector as a linear combination of basis vector. You express this vector as a linear combination of basis vector. So let us say this is some x1 times basis vector. You have to express this in terms of basis vector. So what is our basis vector? 1 0 0 plus x2 times 0 1 0 plus x3 times 0, 0, 1 equal to some, let us say some, let us call this as some x4, right? x4 times 1, 0, 0 plus x5 times 0, 1, 0 plus x6 times 0, 0, 1 some x7 times 1, 0, 0 plus x8 times 0, 1, 0 plus x9 times 0, 0, 1. So this x1, x2, x3, x4, x5, x6 are our matrix for this linear operator. So what is the unknown you have to put here? What is the unknown you have to put here? Let's call this as some x2 and just make it some color so that you will have some understanding, right? If it is a standard basis means you can write this matrix directly, but I'm telling you the general way. Do not confuse. X2, 3, 4, x5, x6, x7, x8, x9. So with each row, you have to find x1, x2, x3. So we'll try to simplify this first row first. So if I do this, what you will have? If uh, if I multiply this, what you will have? X1, comma x2, comma x3, right? Multiply this, you will have x1, comma 0, comma 0, x0, comma x2, comma 0, 0, comma 0, comma x3. So that means these two are equal. That means x1 is 2, x2 is 4, x3 is 2. So I can write this as 2, 4 and 2. You should not simply write this 2, 4, 2 here. If it is a standard basis, you can write this directly. If not, usually what you have to write here is you have to write x1, x2, x3, x4, x5, x6, x7, x8, x9 here. If it is a standard basis, then x1, x2, x3 turns out to be this 2, 4, 2. You solve. And x4, x5, x6. So if you do this, you will have what? x4, x5, x6. And this will be x7, x8, x9. So this is our matrix. If it is a standard basis, then this you can write this as 0, minus 1, 3, 0, 0, minus 1. Yes or no? Because if you equate x4 is equal to 0, xy is equal to minus 1, x6 is equal to 3. So this is our matrix of T with respect to the standard basis. With respect to the standard basis, right? Okay. Is T invertible? You just find the determinant of T. Just find determinant of V. So determinant of 2, 0, 0. And then we have 4, minus 1, 0. So 2, 3 and minus 1. So what is the determinant for this? This is nothing but this upper triangular matrix, right? So determinant is nothing but product of diagonals. So which is equal to plus 2, right? Which is equal to plus 2. So that means determinant of T is not equal to 0. So that means what? T is invertible. See, you can say T is invertible in three ways. One is what? I'll tell you. Just make a note of it. Determinant of the corresponding matrix is not equal to 0. T is invertible. Rank of that operator, rank of the matrix is equal to dimension of R3. That is, if the rank is equal to 3, then also it is invertible. Second thing. Third thing is, if nullity is equal to 0, that is dimension of null space is 0. Nullity is 0 means then also it is invertible. So three ways. One is determinant not equal to 0. Other is rank of this matrix is equal to all are same thing only, because rank plus nullity is equal to dimension of V. So in this case our rank is 3. Our rank is 3. So 3 plus nullity is equal to 3 dimension. So that means nullity has to be 0, right? All are equivalent only. So this is T is invertible. Is T is invertible? Yes, T is invertible. If yes, find T inverse. 10th standard level, 12th standard level mathematics, right? You know how to find T inverse. So T inverse is nothing but 1 by determinant of T into adjoint of T. So determinant of T is 2. And what is adjoint of T? How to find adjoint? So you start with minus 1. So minus 1, minus 1, minus 1, 0, 4 minus 1, 3, 3 minus 1, 2, 3, 0, 0, 2, 0, minus 1, 0, 4 minus 1, and then you have to put transpose. So how to find adjoint is you start with this element minus 1, 0, 4 minus 1, that is the first row, 3 minus 1, 2, 3, second row, 0, 0, 2, 0, third row, minus 1, 0, 4 minus 1, that is our fourth row, third row, and then you have to minus 1, 0, 4 minus 1 is the fourth row. So 1 by 2, so this minus this. So this is plus 1, 1 minus 0 is plus 1. In between you have to put minus sign. So 0 minus of minus 4 is plus 4. 12, 12 plus 2, 14. 0 minus 0, minus 2 minus 0, 0 minus 0, right, sorry, 0 minus 6. This is plus 6. Minus 6, right? 0 minus 6. 0 minus 6, 0 minus 0, 0 minus 0, and then we have minus 2. So this is our T inverse, right? So 1 by 2, 1, 4, 14, and then 0 minus 2 minus 6, 0, 0 minus 2 is our inverse. Is it clear? So we'll move on to the fourth problem. Yes. See, some book they will write this vector in a row, right? This vector in row. That is, I written 2, 4, 2 column wise, right? Some may write in row format, but that's not an issue, right? If they write in row format, they will have this answer as okay, okay. I need to put transpose here, right? Sorry, this is not an inverse, right? You have to put transpose for this. So that means this is 1 by 2 of 1, 0, 0, 4 minus 2, 0, 14 minus 6 minus 2. This is our inverse, right? I forgot that I forgot to put transpose. So 1 by 2, 1, 0, 0, 4 minus 2, 0. Yes, this is our inverse. So we'll move on to the next problem. Okay, 7, 12. Yes. So let V is equal to M2 of R. So we have a 2 by 2 matrix over R. Find the matrix of find the matrix of linear mapping phi from V to V given by phi of V is equal to 1, 2, 3 minus 1 into V with respect to the standard basis of M2 of R. N find the rank of V. Is phi invertible? Justify your answer. Yes. So what is our standard basis of what is our V? V is M2 of R, and let us say what is our standard basis of M2 of R? 1, 0, 0, 0, 0, 1, 0, 0, and then 0, 0, 1, 0, and then 0, 0, 0, 1. Right? This is our standard basis. So we'll put each elements in P of. We need to find the matrix for this basis, right? See, this is same as this problem, right? We already found the matrix for this, right? Already we have found the matrix for this operator, and this operator is from R3 to R3. So the same thing. We have found the standard basis for R3 is 1, 0, 0. So you have to put P of 1, 0, 0. You will have some output. You have to express that output as a linear combination of vectors of bases. That linear combination will be in our column of the matrix, right? Okay. So first we will find P of 1 0 0 0. So what is P of 1 0 0 0? See here T is V, right? Our T is nothing but phi. So what is P of 1 0 0? 1 2 3 minus 1 into 1 0 0 0. So if you multiply, what you will have? So this into this. So 1 into 1, 2 plus 0. 1 into 0, 2 into 0. 3 into 1 and then 3 into 0 0. You have to express this as a linear combination of basis vector, right? So this, let us say this is some x1 times 1 0 0 0 plus x2 times 0 1 0 0 plus x3 times 0 0 1 0 plus x4 times 0 0 0 1. So since it is a standard basis, obviously this reduces to what? This reduces to x1 comma x2 comma x3 comma x4, right? This reduces to x1 x2 x3 x4, right? Because if you multiply, you will have x1 0 0 0 x2 0 0 0 0 0 x3 0. If you add, you will have this, and if you equate, you will get x1 as 1, x2 as 0, x3 as 0 3, and x4 as 0. And similarly, second basis vector 0 1 0 0. So it is 1 2 3 minus 1 into 0 0 1 0 0. So what you will have? So 1 into 0, 2 into 0, 1 into 1, 2 into 0, 3 into 0, 3 into 0. This will be 3, right? So this is, let us say, some x5 times 1 0 0 0 plus x6 times 0 1 0 0 plus x4 times 0 0 1 0 plus x8 times 0 0 0 1, and this turns out to be x5 x6 x7 x8, and similarly if you equate, you will get x5 x6 x7 x8, and phi of 0 0 1 0. So phi of b is 1 2 3 minus 1 into 0 0 1 0. So this into this is 1 into 0, 2 into 1, 1 into 0 0 0, 3 into 1, this is minus 1, and this is 0. Now you have to express this, you have to find x9 into 1 0 0 0 plus x10. See, since the standard basis, finding x1, x2, x3, x4, all these are turns out to be very easy. If it is not a standard basis, means you will be getting some equations here. Now you have to solve a system of equations to get x1, x2, x3, x4. We will do that kind of problem also. X10 times 0 1 0 0 plus x11 times 0 0 1 0 plus x12 times 0 0 0 1. So this turns out to be x9, x10, x11, x12, right? And then final vector 0 0 0 1, so which is 1 2 3 minus 1 0 0 0 1. So this is, what do you have? 1 into 0 0, this is 2, and this is 0, this is minus 1, right? So this is, let us say this is x13 times 1 0 0 1 0 0 0 plus x14. See, I'm always, you have to do in standard format, right? Then only if you do some bigger problems, you will be able to understand. Simply, you should not write 10307. Write it in column. You can write it in column provided if you are operating in standard basis. But why you are doing this? Because usually you should not write this in column. You have to write this x1, x2, x3, x4 in our column. X1, x2, x3, you have to four. You have to find it. How to find x1, x2, x3, x4? X1, x2, x3. So I have to write this vector as a linear combination of basis vector. That linear combination scalars, no, that you have to write in column. Simply you should not write this vector in column. Right? This method works if it is a standard basis. If it is standard basis, then this x1, x2, x3, x4 turns out to be this. It is not true for all. Okay. So x14 times 0 1 0 0 plus x15 times 0 0 1 0 plus x16 times 0 0 0 1. So it turns out to be x13, x14, x15, x16. So therefore, the matrix of T with respect to the standard basis is given by what's our matrix? All those x1, x2, x3, x4, x5, x6. So here it is 1, 0, 3, 0. You have to write x1, x2, x3, x4 here, right? This is our matrix first column. This is our matrix second column. These unknowns are our third column, right? These unknowns are our third column, and these unknowns are our fourth column. And it is very easy to find the unknowns if it is a standard basis. You just have to equate these two matrices. So 1 0 3 0, and here it is 0 1 0 3 2 0 minus 1 0 0 2 0 minus 1. Is it clear? So this is the matrix for phi with respect to this linear operator with respect to the standard basis. Find the rank of phi. So just find the rank of phi. If the rank is turns out to be 4, then it is invertible. Yes or no? We know T is invertible if rank is equal to dimension. Okay. So we will find the rank of T. So what is our phi? Our phi is 1030. Our phi is 1030. Then 0103, 0103, 20 minus 10, 20 minus 10, 020 minus 1. So we'll reduce this to row echelon form. Already this is 0, so we'll make this as 0. So R3 is transformed to R3 minus 3 times R1. So this is equivalent to 1020, 0102. We'll multiply 3 and then you subtract. You multiply 3 and then you subtract. You multiply 3, so minus 1 minus 6 minus 7. You multiply 3 and then you subtract. 0, 3, 0 minus 1. Right? Now we have to see this is not in row echelon form. When the matrix in row echelon form, first row, first non-zero element, below that everything is 0. Yes, it is correct. Now second row, first non-zero element is 1. Below that everything has to be 0, but 3 is not 0. So we'll make 3 0 with the help of this element. So we have R4 is transformed to R4 minus 3 times R2. So this is equivalent to 1020, 0102, 00 minus 7 0. So what we'll do is we'll multiply 3 and then you subtract. You multiply 3 and then you subtract. You multiply 3, this is 6. So minus 1 minus 6 is minus 7. Right? This is in row echelon form, right? This is in row echelon form. Why? First row, first non-zero element, below that everything is 0. Second row, first non-zero element, below that everything is 0. And also third row, first non-zero element, below that everything is 0. And fourth row also, first non-zero element is minus 7, below there is no element. So that means it is 0. So you can see rank of A is equal to what? 4. If rank is equal to total dimension, surely determinant of T will not be equal to 0. So that means T is invertible. Or you can also say like, we know rank of T plus nullity of T is equal to dimension of M2 of R. Dimension of M2 of R is 4 because there are 4 elements in the basis, which is 1 0 0 0 1 0 0. Already you know. So rank of T is 4. So that means nullity of T has to be 0. Nullity of T is equal to 0 means also what? It is invertible. It is invertible. That is 0 vector is the only vector that maps to 0. What is nullity of T is 0. That means dimension of null space is 0. Dimension of null space is 0 means null space null space will only have the 0 vector. So that means 0 is the only one that is mapping to 0. That's what it means, right? 0 is the only one that is mapping to 0. Yes or no? Suppose if some other vector also maps to 0, like in the previous sum. In the previous sum, we see that where is that problem? Yes, in this problem, if you consider, you can see that this infinite set of vectors are mapping to 0. Right? Infinite set of vectors are mapping to 0. Which are the infinite set of vectors? K times minus 1, 1. That is minus 1 maps to 0, minus 2, 2 maps to 0. That means it is not 1 to 1, right? This operator is not 1 to 1. That means it is not invertible. When the operator is invertible, it has to be 1 1 on 2. If it is 1 1 on 2 only, we can define inverse, the reverse map. Then only it will be a function. 12th standard mathematics. So that means if the null space contain infinitely many vectors, surely it is not 1 to 1 because many vectors are mapping to 0. Right? That is the idea. But here you can see, and this also you can see that is the matrix invertible? Yes, it is invertible because our rank is equal to 3. If your rank is 3 means rank plus nullity is dimension of R3, which is 3. So rank plus nullity is equal to 3. That means nullity has to be 0. That means 0 vector nullity 0 means dimension of null space is 0. Dimension of null space is 0 means the only vector is 0 vector is there. That means 0 is the only one that mapping to 0. That means it will be 1 to 1. Right? And for and for finite dimensional vector space, 1 1 implies onto. So that means 1 1 and onto. If 1 1 happens, onto will join with that. Right? Okay. That is the idea. So it is invertible. So what is the question? See, this carries 15 marks. It is just a matter of 5 to 6 minutes if you write. Not even 5 to 6 minutes. If you write elaborately itself, you can do this in 5 minutes. Right? This is how you have to present in exam. Uh, Let B is equal to M2 of R. Find the matrix of linear map. This is a matrix of linear map. Hence, find the rank of P. So, rank of P is 4. Is P invertible? Yes, P is invertible. P is invertible if rank is equal to dimension. Uh, that means rank is equal to 4. If rank is 4 means determinant will be not equal to 0. Or you can also say nullity is equal to 0. That means it is invertible. You can do this in many ways. Yes. So we'll move on to the fifth problem. Is it clear up to now? My video is clear, right? Okay. So we'll move on to the final problem. Let A is equal to 3 to 4, 2 0 2 4 and 3 be a 3 cross 3 matrix. Find the eigenvalues and eigenvector of A and hence find the eigenvalues and eigenvector of A power minus 15. So very simple problem. You know how to find eigenvalues and eigenvectors. So I'll do this very fast. So what is eigenvalue? Eigenvalue is nothing but the roots of the characteristic equation. How to find characteristic equation? Determinant of A minus lambda. You know how to find characteristic equation, right? Determinant of A minus xi is equal to 0. If you expand the determinant, you will get the characteristic equation. Or else you can also use the formula to find a characteristic equation. So what is the characteristic equation? Characteristic equation of 3 cross 3 matrix. Characteristic of 3 cross matrix given by lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. So S1 is nothing but trace of the matrix. What is trace? Trace is nothing but sum of the diagonal elements. Sum of diagonal elements. Sum of diagonal elements. So what is the sum of diagonal elements? 3 plus 0 plus 3. So 6 is our S1. Now what is S2 is? S2 is you just find the minor for all diagonals. So for 3, what is the minor? For 3, what is the minor? 0, 2, 2, 3 plus for 0, what is the minor? That is you have to find minor for diagonal element. So how to find minor? If you want to find minor for 0, omit the corresponding column, corresponding row. So you will have 3, 4, 4, 3. 3, 4, 4, 3. And then what is the minor for next diagonal, which is 3, corresponding column, corresponding row. So 3, 2, 2, 0. 3, 2, 2, 0. So expand this determinant. So it is minus 4. And this is 9 minus 16. 9 minus 16. This is minus 4. So this is minus 15 is our S2. S3 is nothing but determinant of A. So what is determinant of 3, 2, 4, 2, 0, 2, 4, 2, 3. So expand this determinant. So you will have 3 times this into this. So 0 minus 4 minus 2 times 6 minus 8 plus 4 times 4. So this is minus 12. 6 minus 2 is minus 4. This is plus 4. This is plus 16. So 20 minus 8. So S3 is 8. So therefore, our characteristic polynomial is given by lambda cube minus S1 lambda square plus S2 lambda minus S3. Actually, characteristic equation is you should not equate to 0. This is our characteristic equation. If you are equating the 0, you will be getting roots. That is called eigenvalue. So this is our characteristic equation, characteristic polynomial. So lambda cube, what is S1? S1 is 6 lambda square. What is S2? Minus 15 lambda. S3 is minus 8. So this is our characteristic polynomial. So this is a cubic polynomial. So it will have three roots. That roots we will be calling as eigen values, right? That root will be calling as eigenvalues. So lambda cube minus 6 lambda square minus 15 lambda minus 8 is equal to 0. So you can see minus 1 is a root for this polynomial, right? Minus 1 is a root for this polynomial. So the coefficients are 1 minus 6 minus 15 minus 8. So 1 plus 0 is 1. In the division 9th standard, 8th standard, right? Okay. So 1 into minus 1 is minus 1, minus 7, plus 7, 8, minus 8, 0. So already lambda is equal to minus 1 is one root, and the other two roots are given by solving these two equations. Lambda square minus 7 lambda plus 8 is equal to 0. For this, you have to multiply lambda square, lambda constant. So you solve this equation. So lambda is equal to minus b plus or minus root of b square minus 4ac divided by 2 times a, right? Uh, b square minus 4 times 1 into 2, 32, divided by 2 times a. Okay, this minus 8, this plus 8, minus 8. So b square minus 4 times a into c divided by 2 times a. So we will have 7 plus or minus. It will be time consuming problem actually. This you have to do very fast. 20 marks, right? So this is 32. 32 plus 49 is 81. So which is 9 by 2. So 7 plus 9 by 2 is 16 by 2. So 16 by 2 is 8. And 7 minus 9 by 2 is minus 1. So therefore, the roots are minus 1, 8. Therefore, the roots of this characteristic polynomial is our eigenvalues. So the eigenvalues is given by minus 1, 8. eigenvalues are -1, -1, 8. Now what we need to do is also find the eigenvector for this matrix. So we will find eigenvectors corresponding to each eigenvalue. So we will find eigenvector corresponding to eigenvector. So eigenvector corresponding uh, to lambda is equal to 8. So first we will do this. So what is eigenvector? Non-zero vector x is such that ax is equal to lambda x is called eigenvector. So that is a minus lambda I x is equal to 0. This x is called eigenvector. This x is called eigenvector, right? A minus lambda I is equal to x is called eigenvector, where lambda is our eigenvalue. So we'll find this vector x now. So A minus lambda I. So what is A? A is our matrix 3, 2, 4. So 3, 2, 4, 3, 2, 4, 2, 0, 2, 3, 2, 4, 2, 0, 2, 4, 2, 3. Okay, I'm doing PYQ very briefly. What I say, I'm not just solving. I'm just teaching you many ideas also, so that you will have some confidence. I'm just not only sticking to this problem. I'm just circling all the concepts revolved in this, right? So that you will have some good confidence. Okay. My focus is to revise the concept also with the help of PYQs. So 3, 2, 4, 2, 0, 2, 4, 2, 3 minus lambda I. So lambda times I will be 800, 080, 008. And then we have, let us say that vector is some x1, x2, x3, right? Because this x is our R3, right? Is equal to 0 vector. The 0 is 0 vector. Okay, what we will have now? So 3 minus 2 is minus 5. So minus 5, 2, 4. 2 minus 8, 2. 4, 2 minus 5. And then we have x1, x2, x3 is equal to 0. Again, if you want to find x1, x2, x3, it is same as solving the homogeneous system of simultaneous linear equations. So we'll solve this homogeneous system of equations. So first what you have to do, you write this in augmented matrix. See, if you just go to the live section, I have solved many problems how to solve homogeneous system and non-homogeneous system. So we will have minus 5, 2, 4, 0, and then 2 minus 8, 2, 0. So 4, 2 minus 5, 0. To solve this homogeneous system, reduce this to row echelon form. Reduce this to row echelon form. So what I'll do is I'll just make some adjustments here. I'll divide by 2. What you will have, if I divide by 2, what you will have? And then I'm switching R1 and R2. So we will have, if we have 1 in the first row, first element, it will be easy for us to calculate. It is not mandatory to do this. So 1, minus 4, 1, 0. And then I'm switching minus 5, 2, 4, 0. Let us keep this as it is. 4, 2, minus 5 and 0. So we'll make some transformations. So R2 is transformed to R2 plus 5 times R1. R3 is transformed to R3 minus 4 times R1. So this is equivalent to 1 minus 4, 1, 0. So what we'll do is we'll multiply 5 and then we'll add. You multiply 5, what you will have? Minus 20. So 2 minus 20. 2 minus 20. 4 plus 5. 9. This is 0. R3 minus 4 times R1. This is 0. 2 minus 4 minus 4. So 2 plus 16. It is plus 18. And then you will have minus 5 minus 4 minus 9. Right? Minus 9 and then 0. Again, you just add these two rows. So you will have 1 minus 4, 1, 0. You just divide by 9, 0 minus 2, 1, 0. And then you divide by 9 again, and then you add. You will end up with 0, 0, 0, 0, right? This is our reduced row echelon form. And how many free variables are there? So number of free variables. equal to total variable minus rank of A. Total variable is 3, rank is 2. So we have one free variable. So we just transform this to again Ax equal to 0 form. So we have uh, x1 minus 4x2 plus x3 is equal to 0, and then minus 2x2 plus x3 is equal to 0. So let us put x3 to be equal to k. So we have one free variable. So this implies 2x2 is equal to x3, or else can I put x2 to be equal to k? That is not an issue, right? Let us put x2 to be equal to k so that it will be easy. It is good to see. Let us put x2 to be equal to k. Then x3 will be 2 times k, right? Or else we will have some k by 2 by any this. Then x2 to be equal to k, x3 to be 2k, and what is our x1? X1 is 4x2 minus x3. So 4 times x2 is k minus x3 is 2k. So we will have 2k, right? So what is our x for this? Our x consists of our x consists of 2k, 2k, and then what? 2k, and then what is x2? X2 is k, x3 is 2k, right? So if I take k outside, 2 comma 1 comma 2. This is called eigenspace. This is called eigenspace. Eigenspace is spanned by, that is, for this eigenvalue, we have one eigenvector only. See, we have infinitely many eigenvector, but basis has only one vector. Basis has only one vector. That vector is 2, 1, 2. So, what is the dimension for this eigenspace? Eigenspace is nothing but in set of all these vectors is our eigenspace. Eigenspace consists of, this is called eigenspace. This is called eigenspace. This eigenspace has infinitely many vectors, but that all those vectors are spanned by only one vector. So what is the dimension of this eigenspace? 1. That is called geometric multiplicity for this eigenvalue. What is the arithmetic multiplicity for this eigenvalue? 1. Because 8 is appearing only one times. Number of times 8 repeats is the arithmetic multiplicity. What is the arithmetic multiplicity for minus 1? It is 2 because minus 1 is repeating 2 times in the eigenvalue. What is the arithmetic multiplicity for 8? 1. What is the geometric multiplicity for 8? It is 1 again. What is meant by geometric multiplicity? So that is geometric multiplicity of this eigenvalue is 1. What is geometric multiplicity? It is nothing but number of linearly independent vectors in your eigenspace. Number of linearly independent vectors in your eigenspace. So eigenspace has one linearly independent vector. That means geometric multiplicity corresponding to lambda is equal to 8 is given by 1. Right? These are extra facts. Okay. So the eigenvector corresponding to lambda is equal to 8. You can is given by, you just write one matrix in column form, that is alone. So 2, 1, 2 is our eigenvector. Any one you can write, or else you can write 4, 2, 4, anything, right? So 2, 1, 2 is our eigenvector corresponding to lambda is equal to 8, right? Okay. So 2, 1, 2 is our eigenvector corresponding to lambda is equal to 8. Okay. Now, what we'll do is we will find eigenvector corresponding to lambda is equal to minus 1. Eigenvector corresponding to eigenvector, I'm telling many additional facts. That's why it is taking time, but not an issue, right? The thing is you have to understand to the core. Eigenvector corresponding to lambda is equal to minus 1. What is the arithmetic multiplicity for minus 1? It is 2 because minus 1 is appearing 2 times. So we will find eigenvector corresponding to this. So a minus lambda I of x is equal to 0. This x is called eigenvector. Eigenvector is always an infinite set also. So a minus lambda I. So what is a? A is 324202, 324202, 324202, 423 minus lambda I. Lambda is minus 100, 0 minus 10, minus 1 into x. Let us say x1, x2, x3 is equal to 0. So this is what? So 3 minus 1. 3 minus of minus 1 is 4. So 2 minus 0 is 2. 4 minus 0 is 4. 2 minus 0 is 2. 0 minus of minus 1 is plus 1. 2 minus 0 is 2. 4 minus 0 is 4. 4 minus 0 is 4. 2 minus 0 is 2. 3 minus of minus 1 is plus 4. And then you will have x1, x2, x3 is equal to 0. So we will find x1, x2, x3 solution for this. That will give our eigenspace. In that eigenspace, you find number of linearly independent vectors. We will do this. So this is equivalent to. So we'll divide by what I can do. Okay, let us keep this as it is. So we will have. We are having these two to be same. 324 423. 324 202 423. Okay, so 324 will be 4. This will be 3. Okay, we're getting these to be same. Okay. So what we can have is we do like 2120. I switch these to 4240 and then 4240. If I try to reduce this to row echelon form, R2 is transformed to R2 is transformed to R2 minus 2 times R1. R3 is transformed to R3 minus 2 times R1. So this reduces to 2120 0, 0, 0, 0, 0, 0, 0, 0, right? So this is in row echelon form. And what is a rank? Rank is 1, right? So we'll find a solution for this. So number of free variables. So number of free variable is n minus rank of A. So n is 3, rank is 1. So we have two free variables here, right? So we have two free variables here. Let us put x2 to be some k1, x3 to be some k2. We'll solve for x1. So we'll write this as equations. So we will have 2x1 plus x2 plus 2x3 is equal to 0. So 2x1 is equal to minus x2 minus 2x3. So minus k1 minus 2 k2, or I can put x1 to be like, or else see all are same only, or else can I put x1 to be, or else can I put like I don't want this division here, so that it looks something not good for me, right? You can do that also, but I do like, let us put uh, let us put x1 to be k and x3 to be some k2, right? You can assume any two free variable to be in your own, right? Just for some simplicity, in simple form, I'm putting x1 to be k2. So that means you will have 2k1 plus x2 plus 2k2 is equal to 0. That means x2 is equal to minus 2k1 minus 2k2, right? So therefore, our solution space is given by x1 comma x2 comma x3. So x1 is k1 minus 2k1 minus 2k2, and it is what is k3 x3, it is k2. This is our solutions, right? This k1 k2 belongs to real number. You can check it. You take k1, k2 both to be equal to 1. If both are equal to 1, what one of the solution is what? 1 comma minus 4 comma 1, right? If k1 k2 both are equal to 1, 1 comma minus 4 comma 1, you see whether it satisfies or not. You see whether it satisfies or not. 2x1 plus x2 plus 2x3 is 0, right? So you put x1 to be 1. So what do you have? 2 times 1, 2 times 1 again 4 minus x2, which is 0. So it is satisfying. Can I write this as some k1 times, here k1 is 1, here k2 is minus 2, here there is no k1 term, plus k2 times, here there is no k2, here it is minus 2, and here it is 1. Yes or no? You can see there are two linearly independent vectors in this eigenspace. In this eigenspace, right? There are two linearly independent vectors, right? So what is our eigenvector? This is our eigenspace. This is our eigenspace. So lead to a eigenvector corresponding to lambda is equal to minus 1 is given by 1 comma minus 2 comma 0 and 0 comma minus 2 comma 1. So these are the two linearly independent vectors. Any linearly independent vectors, any linear combination of this also, k1 times this comma k2 times this also a linearly independent vector. But I take one. So these two vector is our basis for eigenspace corresponding to lambda is equal to minus 1. Already we know dimension of eigenspace is our geometric multiplicity. What is our geometric multiplicity for minus 1? It is 2, because the eigenvector eigenspace corresponding to that eigenvector has two linearly independent vectors. What is the arithmetic multiplicity for minus 1? It is again 2. I'll tell you one more fact. For the first eigenvector corresponding to lambda is equal to 8, gm is 8, am of 8 is also 1. For the first eigenvalue, am of that eigenvalue is 1, gm of that eigenvalue is 1. So am is equal to gm, am is equal to gm for this eigenvalue. Again for next eigenvalue also, am is equal to gm. If am is equal to gm for each eigenvalue, we say that that matrix is diagonalizable. Actually, the topic is deleted, I think, in your replay syllabus for the past 1 or 2 years. Whenever you need to show a matrix is diagonalizable, follow the same procedure. You say after this, you say that there are two eigenvalues, two distinct eigenvalues. Minus 1 is one eigenvalue. For minus 1, our arithmetic multiplicity is 2 because minus 1 is repeating 2 times. And for minus 1, your eigenspace has one linearly independent vector. That means gm is also 1. What is gm? Gm is our dimension of eigenspace. And for uh, okay, for 8, our gm is 1, am is also 1. And for minus 1, am is also minus 2, gm is also minus 2. Right? Okay, these are some additional facts I'm telling you. See how the beauty of linear algebra. Right? Actually, I'm strong in linear algebra. Okay. So, what is our eigenvector? Eigenvector matrix. Eigenvector matrix is given by, so you just write those vectors in column form. Eigenvector corresponding to lambda is equal to 8 is what? 2, 1, 2, right? 2, 1, 2. This is our eigenvector corresponding to the first eigenvalue. And for eigenvector corresponding to lambda is equal to minus 1 as two vectors, you write it here. 1 minus 2, 0, 0 minus 2, 1. So this is our eigenvector matrix, we will say. So eigenvector corresponding to lambda is equal to 8 is 2, 1, 2. An eigenvector corresponding to this is 1 minus 2, 0, 0 minus 2, 1. Is it clear? Is it clear? Okay. Okay. Use our eigenvector matrix, but you don't want to write this actually. Eigenvector corresponding to lambda is equal to 8 is given by uh, these are eigenvectors, right? 2, 1, 2. An eigenvector corresponding to lambda is equal to -1 is given by these two, right? Okay. Now what they asked is also find the eigenvalue and eigenvector of a power minus 15. Eigenvalue and eigenvector of a power minus 15. Eigenvalue and eigenvector of a power minus 15. The eigenvector of a power n, eigenvector of a is same as eigenvector of a power n. That's a property. You just quote the property and then you write. And then eigen, these are just properties of eigenvalue. If eigenvalues of a is, let us say, lambda 1, lambda 2 and so on up to lambda n, then eigenvalues of a power minus 1 is given by lambda 1 power minus 1, lambda 2 power minus 1, lambda n power minus 1, and eigenvalues eigenvalues of a power n is nothing but lambda 1 power n, lambda 2 power n to lambda n power n. You can just power directly to the eigenvalues. Now we need to find and also eigenvector of a is same as eigenvector of eigenvector of a power n is same as eigenvector of a. These are just properties of eigenvalues. Now we need to find the eigenvalues and eigenvector of a power minus 15. So eigenvalues of a power minus 15 is same as, what is the eigenvalues of a? -1, -1, 8, right? So -1, -1, 8. You just raise minus 15 to the power, right? That means -1, -1, 1 by 8 power 15 is the eigenvalues for a power minus 15, right? And eigenvector of a power minus 15 is same as eigenvector of a. See, what is eigenvector? A non-zero vector x such that ax equal to lambda x is called eigenvector. Now, what about a square x? A square x is a into ax. So a into, what is ax? What is ax? It is lambda x, right? I can do like lambda x. So lambda into ax. And what is ax? Lambda x. So which is lambda square x. So a square x is same as lambda square of x. X is same for both. So a square is equal to lambda square of x. So eigenvalue of a square is lambda square. And the x is same. So eigenvector remains same for a square. So it is true for any n. So a power n of x is same as lambda power n of x. So that means eigenvalue of a power n is nothing but lambda power n. and x remains same for all. That means eigenvector will remain same. So that means this is a proof for this. Simple proof only. So that's it. So we are done with all the problems. See how easy it is, right? If you know the concept, this carries 15 marks, fraction of just a matter of minutes, and this carries 20 marks. Nothing tricky, just calculations. And then this carries 15 marks, nothing. And then this carries some 10 marks. So you can see 70 marks how easily you can get in linear algebra if you know all the concepts, right? So in the next class, what we'll do is we will solve 2023 paper. So I have discussed 2024 paper. So next class I will discuss 2023 paper. So I'm discussing very elaborately so that you will have a good confidence even if some new problems are having, right? So we'll see in the next class. Thank you. All the best. Bye.